It is better known as NSGA-II. Just to give you a brief background of why we should study this algorithm rather than any other multi-objective genetic algorithm is last year this algorithm was adjudged as the most fast breaking paper by IEEE. It has till date got more than 250 citations, and given the time that it was developed during 2000 of October of 2000, that's a pretty fast breaking paper. Actually, we have got a lot of citations. Let's go to the PowerPoint presentation. Okay. Typically, most of the problems what we deal with are multi-objective in nature. We have more difficulty in solving these particular problems if we have conflicts. Like if I have a problem in which I have to say minimize both of the objectives, but my design is such that if I try to minimize one particular objective, other one grows, then it is typical conflicting objective type multi-objective optimization problem. A example of this particular class is like if we have cars, if my objective is to maximize luxury and to minimize the cost. So, we can clearly see that this is a multi-objective optimization problem where we have conflicting objectives. For example, if I would go for a higher luxury car, it will cost me more, whereas the lower price car will not have as much luxury. We can clearly see that there is no single solution for this. The mathematical formulation of multi-objective optimization problem is given here. Like fx is the objective function and which is a vector. In single objective optimization problem, we have a single function there, and we can have constraints both equality type and inequality type. As I have said, multi-objective optimization problem cannot have a single solution because we cannot say one solution is better than other unless we have a particular bias towards that particular solution. So, in this case, we get many optimal solutions. Like if you see the chart on this side, we have a problem where we want to minimize both two functions f1 and f2, and this is the function space representation of the functions. So, if you see here, I cannot say that there is a single optimal point. Instead, all the points which lie on the boundary here are optimal. That is, if I consider this point and this point, I cannot say this one is better in f1, but it has a very high value of f2, whereas if I consider this point, it has a low value of f2, but higher value of f1. So, we cannot clearly say that one is better than other, it is a matter of choice. In this for a multi-objective optimization problem, we have all these solutions which are these trade-off solutions. They are known as Pareto optimal solutions, and if we do a function space representation of these solutions, that is Pareto optimal front. For a two-dimensional problem, like when we have two functions, the Pareto optimal front is a curve. When we go to higher dimension, we get hypersurfaces. The usual approaches to solve multi-objective optimization problems is to convert it into a single objective optimization problem. For example, we can use the weighted sum. Like we can assign a weight which is proportional to what we want to get, and then convert a multi-objective optimization problem into single objective and then solve it. Another method, I think what you have studied over here also, is epsilon constraint strategy, in which you say that my one objective is my objective function and all the other objectives are my constraints. So, for a particular value of constraint, you solve for the objective function. The other popular strategy is multi-objective genetic algorithms. Just to give you an idea why we should we want to use genetic algorithm rather than the other classical strategies is in order to get a lot of trade-off solutions, which is actually our objective, we have to run the single objective optimization, solve a lot of single objective optimization problems, whereas when we solve the multi-objective optimization problem using GAs, we can get a lot of trade-off solutions in one single simulation, because this is a population based approach. typically what we look for a algorithm to be good. In single objective optimization case, there is only one requirement. If we can converge to a single objective optimization solution, that is what we need. Whereas in case of multi-objective optimization problems, we have two requirements. First is we should be able to converge to the optimal solution, and second, we should be able to get a good spread. What I mean by spread is, since let's see for this particular example, we have this extremity and this extremity, which are probably the optimal solutions when I just consider one individual objectives. In between all of these solutions, which are shown by these red dots or lie on this particular curve shown by thick line, are optimal solutions. Ideally, we would like to get a uniform distribution of solutions which cover entire zone from here to here. So, that is what I mean by spread. Okay. Is there any question related to this? Okay. Before I go on discussing the details of multi-object NSGA-II, that is non-dominated sorting genetic algorithm, let me define a couple of terminologies. First term is non-domination criteria. In single objective optimization problems, we have only one objective. So, we can compare two solutions, and we know if my function value for one objective is better than other, I can say that one is better than other. But in multi-objective optimization case, it is not that simple, because we have two objectives, and one objective may be better in one objective, whereas other one is may be better than other objective. So, how to compare them? I will explain this by use of this figure. Let us say we have this point and this point. Here we see that this point has low f1 and relatively high f2 when I compare it with this point. So, I cannot say one is better than other, whereas if I compare this solution with this red solution, I can see that red solution is better in terms of both objectives than this solution. So, this blue solution is dominated by this red solution, or in other terms I can say that my red solution is non-dominated with respect to this blue solution. So, this is a twisted terminology, but it will be more clear as I will explain. Now, if I compare this solution and this solution, still we cannot say that one is better than other. So, both of them will still be considered non-dominated with respect to each other. However, if I consider all the solutions in this space, my criteria of defining a solution as non-dominated will depend on all the points in the space or in the set what I am considering. So, the definition will be, if a point is not dominated by any other point in the set, then this point is considered as non-dominated point. For example, if I consider this blue solution, and if I compare it with this solution, this is non-dominated. However, if I compare this solution with this red solution, then this is dominated. So, I cannot say, well, so in this case this solution is not a non-dominated solution, because there exists a solution which dominates this. However, if I consider any of the red points, I can see that there is no solution which dominates these red solutions. So, those solutions will fall in the category of non-dominated solutions. It is very important to recognize at this point that this is relative to the set. If, say, I remove all the red solutions, then I can see that my blue solutions will fall in the category of non-dominated points. Is it clear, or do you need have? Yeah?
I have a question. The red points on front, those points are all dominating points?
They are all non-dominated points rather than dominating points.
So they can dominate points? within the domain.
Yes, they are better than the solutions, or they are which are inside the domain, or no other solution is better than them. It's a little confusing to say that they are dominating point or they are better than others, because if I compare a red solution with any other red solution, this is not really better. Whereas if I say that they are not dominated by any other solution, then it is a correct representation. Okay. Yeah. Any other question? Okay. Next thing what I would discuss is ranking. Ranking is one of the ways how we do the selection in multi-objective genetic algorithms. In single objective optimization case, we have two objectives which we compare. If one is better than other, we can select one. Whereas when we go to more than one objective, we have to devise methods to compare the results. One method is based on this non-domination criteria, that is, we assign the rank. For example, if I consider this particular solution set, so all my non-dominated solutions are the best. They are the solutions which I would prefer if I have to stop at this particular instance, and so they are called as rank 1 solutions. Now, if I remove all these red solutions and find out the other level of non-dominated points, they will be my rank 2 solutions, okay, and so on till I exhaust, go and find out all the assign each solution a rank. So in this case, we can see that we have rank 1 solution which are red, rank 2 solution which are blue, rank 3 solutions which are pink, and rank 4 solution that is blue. Okay. Is there any question with respect?
All the green part is the feasible domain, right?
Yes.
So you are talking about ranking because you have found only these points. If you find some other points, let us say that some other point on the boundary, then it would definitely have a higher rank than the one which is. So there are some red points in the boundary.
Yes.
Red solution. So if we consider a boundary close to that, a bottom boundary, then that would be the rank 1.
Yes.
So you are doing the ranking only among the solutions that you have found till now. It's not.
Yes. The ranking and non-domination search is done only based on the current solution set. I can, as I go on searching for the solutions, I can still find solutions which are better than what I have already. Like for this example, if I consider this particular point, at a later stage of search, I may find out a solution which is, say, at this point, which will clearly dominate this point. Then this solution will no longer be a non-dominated solution. So it is at a particular generation or solution step, I find a set of solutions and I classify them in dominated solutions and non-dominated solutions and do the rankings accordingly. Okay. Okay. What we have done using ranking and non-domination search, we have found a way to push our solution set towards the Pareto optimal front. That is, we have taken care of convergence. However, it still does not guarantee me the spread on the front. So what I would like to do here is, I should, in order to find out a good multi-objective optimal solution, I should find out the Pareto optimal solutions which are spread out. Like I can still have non-dominated solutions which are, say, in this region, all my solutions are converged in this region. They all will be the converged solutions, but that will not be considered a good solution because I could not find a solution in this region. So in order to assist the algorithm to spread out the solutions, what we do is there are two approaches. First is the parametric approach and second is non-parametric approach. Niching is a parametric approach. What I mean by niching is, for each solution I reduce, if it is crowded by a lot of points, then I specify a radius, niching radius. If a lot of solutions fall in this particular radius, I would reduce the importance of this particular solution by the number of points what I have, or by some means I will reduce the number of the fitness of this particular solution such that it takes into account that it is crowded by a lot of solutions. So essentially what I am doing is I am saying that, okay, you have found this solution that is good, but try to find out the solutions which are far from this. This approach is parametric, so we always have a dilemma of choosing the correct parameters. Whereas the other approach what we use in NSGA-II is the crowding distance. This is a non-dominated approach, this is a non-parametric approach. Let us say we have for each solution we assign a crowding distance. How do we compute that? Let us say we have this particular solution. We have two neighbors, first is this and second is this. What I do is I find out the linear distance between its neighbors, that is this point and this point, that is A, and on the other side the distance is B. That means I do a linear computation of differences between objectives for each dimension, each objective dimension, and then I do a sum of the distances. That will be its crowding distance. That is, the crowding distance of this particular solution is C, that is A plus B. If I go to ends, I have only one neighbor. So in that case, I assign this solution a infinite crowding distance. That is, I want to preserve this solution and I want to move away from, or if I can move towards outwards, that will be a better. Okay. Practically when we implement it, we do this by assigning a very large number which we can consider as infinity. It will be more clear how is this going to be used when I go to the algorithm description. Okay. Next thing what we have is that is elitism. Okay. I don't know why some of the things which should have been here. Okay, now it is there. The elitism is a criteria by which we give importance to the good individuals, like, or good solutions. Like say, I have one solution set from which I generate another solution set. First one is considered parent population and second one is the child population. So I would like to keep all the solutions which are best. I don't care from which set they are coming from, because during the search process I don't want to lose the best solutions. That will help me in converging to the final solution. So let us consider that we have these red solutions in this figure coming from parent population and these blue solutions which are in the child population, and I have to select a set of solutions that would be the same as my population size. Let us say for my parent population I had 10 solutions, I created 10 children from that parent population. Now I have 20 solutions. Since I have to go to next generation of GA, I cannot take more than my parent population or the population size, that is 10 in this case. So I have to select 10 out of these 20 solutions. So in this case, if I do a ranking on the combined set, I can see that some of the solutions I can ignore. Like if I see here, this solution in the child population is dominated, so I can probably ignore that. Similarly, this solution is dominated which was in child population, whereas this solution which was then parent population is still not good. So you can see that all the points which are circled are selected after elitism, and they are the best solutions with respect to this solution set of 20 points. Okay. Is this clear, or you have some questions?
I have a question. So the ranking criterion is used to differentiate the better points and the normal solutions. Am I correct?
Yes, ranking is used for identifying the best solutions. All the rank 1 solutions are considered the best, and compared to the ranking what we did just a few minutes back, that is based on one single population. Now here we have combined two populations, and now we have done the ranking on a set of solutions which is twice the size of individual population. Okay. Yeah.
To provide the problem of neighbor points, you change the rank of your bad point, like in the previous graph. You identify when the points are too near.
No, in this case, actually that's a very good question. In this case, first of all we do the ranking, and if say I have 10 points in parent population, which out of which 4 are on rank 1, 3 are on rank 2 and 3 are on rank 3, and I create a child population which has say 4 or say 5 solutions which are on rank 1, 2 solutions on rank 2 and 3 solutions on rank 3. When I combine these, I have to rank it again. Now let us say I have 6 solutions which are on rank 1 and say 5 solutions on rank 2, 5 solutions on rank 3 and remaining on rank 4. So I can right away pick 6 solutions which are on the rank 1, and since in rank 2 I have 5 points, but I can only pick 4 points. So I have to use crowding distance. That is how I maintain that bring in the nearness criteria over here. I select the solutions which are far spread, or in other words which have higher distance compared to their neighbors.
Tushar, I'm not sure that it's clear to people, but the rank is used in selecting parents, isn't it?
Rank is used in selecting parents as well as going to finding out the next generation solutions.
Yes, but the parents, the first time that you use rank is when you select parents to create the child population.
Yes.
Okay.
It will be a little more clear when I will go to the algorithm of NSGA-II. Okay. Any other question? Okay. Okay. Let's consider this as a flowchart of NSGA-II. We start with a population. It's of size n. We initialize it, compute the objective functions, and if we have constraints, we do that. Then we rank the solution, the population. Now we use this rank to do the selection. Now I have selected the solutions for mating that will go to the crossover pool. Okay. Now I do the crossover and mutation. After that, I get another solution, another set of solutions. That is my child population. That is actually an intermediate child population. Okay. For this child population, I do evaluate the objective functions. Now I have a population which is this, that is a child population, and I have a population here that is a parent population. I combine both this solution, this population and this population here. That is, I get a combined pool of 2n size of solutions. Now I do a ranking on this set of 2n solutions, and I select n individuals. This is elitism. Okay. So we have used ranking first time here to select the mates. Second time ranking is used here to find out the next generation population. Okay. To explain, yeah, I am going to next is just to explain the elitism process. Let us say I have, this is my first population, that is my child population. These are rank 1, rank 2, rank 3, rank 4 and so on solutions, and this is the parent population which has different ranks. When I combine them and rank them, I get this solution set where we have rank 1, 2, 3 and so on. Now I have to pick n solutions, and if you see that let us say I can select only n solutions, I will pick say all of rank 1 solutions. Second, I pick rank 2 solutions. Now, I have, let us say this was 60, let us say we have the population size of 10, we had 6 solutions here, 2 solutions here and 4 solutions here. So, I have already picked 6 over here, I have picked 2 over here, and this is the space where I have space for 2, but I have 4 options. Now, I look for the solutions which have high crowding distance. Okay. That is how I use crowding distance over here. Another place where we do use crowding distance is selection. Now, say I have 2 solutions which one is on rank 1, other is on rank 2. Clearly, I can select rank 1 solution. However, when I have 2 solutions, both of them are on rank 1, how can I select them? Then I try to look for the solutions which provide me better spread. In this case, that is crowding distance. So, I select the solutions which are less crowded or have higher crowding distance. Okay.
So do you use tournament selection?
Yes, I do use tournament selection.
So how do you create the child population here?
Okay. This I have, after doing the elitism, this solution is the child population.
No, I mean in the flowchart, how do you create the child population from the rank population of parents?
Okay. I do use selection and I choose the mates for crossover. I do the crossover and then I do the mutation. The solution what I get is an intermediate child population, because I want to keep the elites. So, I have to still go back and then look for the best solutions in my parent population also. Okay.
So how do you make them? You choose 2 rank 1 points and then made
No, I don't. Once I have done the selection, I have found points or a solution set, out of which I will randomly pick solutions for the mating. I don't specify a criteria such that only best will mate or something like that.
But
That is already taken care of when I do the selection.
Why don't you explain the tournament? The one that I thought was the roulette wheel. So
Oh, okay. Okay. Let me explain with the help of the board here. Let's say I have a population set. I have 6 solutions. This is rank 1, this is rank 2, rank 1, rank 3, rank 2, and rank 1. And when I do the tournament selection, I randomly pick 2 of the solutions from this set. For example, I draw this and I draw this. So this is rank 1 and this is rank 3. I pick one of them, that will give me the rank 1. I will select rank 1. Second time what I do is I pick this and this. So 2 versus 1, I get 1. Okay. If I happen to pick this and this, that is rank 1 versus rank 1, then I have to look for their crowding distance. Let's say in this case it has a crowding distance of 10 and it has 8. So I will obviously prefer the one which has rank 1 with crowding distance 10. And here, in order to be fair with all the solutions, what I do is I give each solution a chance twice to mate with other solutions. So in that case, this will have 2 chances to be picked, and this will also have 2 chances. So from here, I have 6 solutions, and again I have to generate a solution set of 6 points. So we can do that. Okay. Yeah.
Yeah, I have another question. So how do you rank the population in details? Because how's rank 1?
How do I rank the population? Okay. Let me go back to the previous slide. Okay. In this slide, I do the non-domination search. All the solutions which are non-dominated with respect to current population set are assigned a rank 1. Okay. That is easy part. Now I remove all the rank 1 solutions from my solution set and do again a non-domination search. Find out which are non-dominated solutions, they will be my rank 2 and so on. Okay. Any other question? Okay. So once I have done the elitism, I again have got this population which I call as the children population. Now if my stopping criteria is met, I stop and report the final solution population. That will be my Pareto optimal solution set. If not, I go back to selection. Now this child population becomes the parent population, and we do repeat this for a number of generations or till our stopping criteria is met. Mostly I use ranking as the number of generations as my stopping criteria. Let me go to walk through an example which is very simple. Here I have a plate which is this plate, and I want to design a bicycle frame from this. I have two objectives. First is I want to minimize the weight of my bicycle frame. So what I do is I minimize the area. Second is I want to minimize the maximum deflection that can happen on my frame. I have three constraints. First is I should get a valid bicycle frame. It should not be a frame which does not have any I have eliminated whole of the plate. That will give me the lowest solution, but that does not give me any bicycle frame. Second is my maximum stress should be less than allowed stress, and my maximum deflection should be less than allowed deflection. Now to give this plate a reality is I should have a place where I should place the seat, that is specified by this location. I have put a loading there. My rear axle is located at this point. I have a place for paddle and I have a place for handle. So these are the locations which I want to be in my bicycle frame. In order to accommodate for the front wheel, I have removed this section of my plate. This is a topology design problem actually. Okay. Now how do we represent this in a format which GA can evolve? So what we do is we divide this whole of the frame in blocks, like these small blocks. You are seeing these checkerboards. For each checkerboard I assign a value 0 or 1. If it is 0, then it means that there is no material. If it is 1, then the material is present. So I can get a binary representation of this particular frame very easily by this strategy. Like if I consider this case, I have a typical binary string like this, and if I put the values here, like this 1 will take 0, 2 will take 1, 1, 1, 0 and so on. So for corresponding to this string, I get a shape like this. Okay. Same way I can represent my bicycle frame, the string size will be different. Okay. The material properties and GA parameters are given over here. So you can see that I have changed the string size to accommodate for my bicycle frame. I have a small population size, that is 30, and I run this GA simulations for 150 generations. After that I get a Pareto optimal solution set. So if I do the function space representation, I have weight on x axis and scale deflection on y axis. So you can see here that I have different solutions which are here. The interesting thing to note over here is I observe that if I allow a small increase in weight, I can reduce my deflection substantially. So that tells me something about the nature of the problem. However, if I keep on increasing my weight, I get very low deflection, but that frame is very heavy. Okay. If I go to the solution, how these solutions look like, here I have picked 5 representative solutions. So this one is with respect to the least weight, that is we have maximum deflection for this particular solution, whereas this solution has least deflection, but it has very high weight. You are seeing here that it doesn't look like the checkerboards what I had previously. The reason is I have also used some smoothing components, like rather than having a point connection between the blocks, I have put some triangles over there so that my shape becomes slightly smoother. But still, since my grid size is not very fine, I have much coarse looking shapes, like we have sharp edges over here, which you will probably never observe in a bicycle frame. If I will use a fine grid, then I can get rid of these things. So we can see here, if I look on all different shapes, we can see here that my weight is continuously increasing, and I get correspondingly my deflection will decrease. So we can see here, from here my evolution takes me to this location from here to here. That is, I have an added stiffener over here, which will reduce the deflection, though it has a cost of increasing the weight. Then I also see that this rear section becomes heavier, so that further reduces deflection, but as we can see that weight has increased, and so on. So we can see that we can get different conceptual designs very easily in one single simulation, which probably is very difficult to get if I start with a specification of preferences upfront. Now we can take these conceptual designs and then do a final design on these particular solutions to get what we really want to. Yeah.
So the initial binary string you select is random. You just
Yes.
randomly pick it.
Yeah. It's same as any GA. We start with a random population and then evolve over the iterations. Okay. Are there any questions related to this? Yeah.
Can I ask a question about the flowchart again?
Yeah.
So how do you select the n individuals from the combined population? Yeah.
Okay. From this combined population, that is, let's go to this chart. Let's say this is n, this child, and this is population of size n. I have 2n solutions over here. I do the ranking, and I have rank 1, 2, 3, so on. I have to pick n solutions. So all my rank ones go here in the new population. I have not yet completed filled space for n individuals. So I pick rank 2 also. Now I have, for rank 3, I have less number of spaces than the candidates. So I use crowding distance to select fill this many spaces. That's how this solution set is my final solution, that is n solutions.
So you always choose individuals within first 3 ranks.
Can you please repeat again?
So you always choose individuals within the first 3 ranks.
Not always. In this case, it happens to be just 3 ranks. However, you can have the situation when I have very few solutions on rank 1. So I can go from rank 1, 2, 3, so on to 4 or 5. It's just a representative case. The criteria of selecting the ranks is till I get n solutions. Yeah.
When you combine the parent population and child population, you have to rank again in the second.
Yes.
Right.
Yeah. Because now my set is different. So the solution which may be non-dominated in one set may not remain non-dominated. Any other questions? Yeah. For elitism step, we don't use tournament selection. That is used just in the selection step. Here we just pick. This process is not random because we want to preserve all the best solutions which we have found. Yeah.
So when you use the tournament selection for selection step, there is a chance that one point is selected 2, 3 times.
Yes.
So what then you don't have an n number of solutions? How do you do that?
We will. Okay. Let me take this example and work it out in detail. Okay. Let's say I I have these solutions, and I assign the rankings, crowding distance accordingly. Okay, and I assign a number to each. Now, I randomly I shuffle my population, and then from 1, 2, 3, 4, 5, 6, I get a combination like this. Okay, I compare 1 and 2, 1 and 3, and I pick 1 with 10. Okay, from 4 and 2, I pick this which has this solution, and this solution is compared. So I pick this solution. Between 5 and 6, I do between 2 and 1. So I pick this solution. Okay, so I have got half of the population. Okay, I do a shuffling again, and I generate other random numbers. Okay, let me. Okay, so now I am comparing 1 and 5. 1 and 5, I pick 1 with 10. Okay, 3 and 4. Okay, so I have 1. 6 and 2, that is this. Okay, this was not a very good solution because I should have got rid of one of them. Okay, so I have 1 and 20. So now this will make my population. In this case, it happened to be that I have many ones than I would have liked to.
So at this point, the first two are the first two parents, and 3 and 4 are the next two parents. So for the crossover,
I can do a random shuffling again. So these are 1, 2, 3, 4, 5, and 6. I do random shuffling again and then pick randomly. Okay.
but in the crossover, I guess what I'm trying to say is that will each one of those individuals get to be a parent?
All these individuals are parents.
Okay.
So my
You will just reshuffle them.
yes, my this population pool is rank 1. Then I don't do a ranking over here now. Okay. So from this, I will do a crossover. I will randomly pick 2 and do a crossover. However, I make sure that each individual gets a chance.
Yeah, but that's what I was saying, that 1 and with the 10, that happens twice. So
Yes.
So the same point is like two.
Yes, right. The objective of selection is to get rid of the bad solutions.
Okay.
So here what we do is my best solution will get 2 copies.
Okay. Oh yeah. So if it is good, then you can use more.
Yes, it has got more chances.
Do you let it mate with itself?
No. So now let's say if I have to do, again I have the numbers 1, 2, 3, 4, 5, 6. I generate another string which is say 1, 4, 3, 2, 6, 5 and 2. So 1 will mate with 4, 2 will mate with 3, this, and then I generate another, well, this will give me 2 children. So that's how.
But in this example that you gave, if you picked 1 and 4 as parents,
Okay,
they
yes.
will be identical. Will
Yes.
you permit that?
Yeah, I don't specifically stop them from doing that. Because still I have a probability coming over here. So even though I have selected them as parents, that's no guarantee that they will get mated. What I meant previously was I don't let 1 with mate with 1. Yeah?
What advantages does using Elitism give you over like a similar function that doesn't use the parents, like only considers child? Has there been any comparison between the two algorithms?
I'm sorry, I didn't get you. What exactly?
Like I'm assuming genetics normally just take the child populations that you get from the parents and then select from those child.
Okay.
You're saying you select from the child and also if there's
Right.
the parents and keep those also.
Yeah.
Has there been any?
Okay, I see. The advantage of introducing this step elitism is I improve the convergence rate to my final solution. If I can still probably get a good set of Pareto optimal solutions by just going through child populations, but I have to allow it for evolve for a longer time.
So you see faster convergence?
Yes, it has a faster convergence. Yeah, and sometimes it is difficult to get the convergence just by using child population.
Let me amplify on that. In a regular GA, there is only one point, which is rank 1. And then whether you transfer it to the child generation or not, it's mostly a matter of aesthetics. You guarantee monotonic convergence instead of the possibility of losing the best and then finding it again. Statistically, it is not shown to be better. But when you have a multi-objective algorithm and you are trying to create an entire front, then losing all the people that you identified on the front is a much bigger disadvantage, and so there is a much more incentive for elitism than in one objective GA.
So I have shown one example on bicycle design, but there are a lot of applications of multi-objective GA in mechanical components like gear design, turbo machinery like injector design, bioinformatics for protein unfolding. People have used this. VLSI circuit designs for electronic packaging problems, traveling salesman problems also, and there are a lot of applications actually. So, okay. There are some more topics which may be of interest is real coded genetic algorithms. Like I have shown the example where we have dealt with binary representation. We can also use the real numbers directly. There are a lot of other multi-objective evolutionary algorithms like evolutionary strategies, that is Pareto archived evolutionary strategies, strength Pareto evolutionary algorithm. There is a latest one which is epsilon MOEA, that is epsilon multi-objective genetic algorithm, evolutionary algorithm. And the other one which I prefer a lot is hybrid GAs. GAs are pretty criticized because of high computation time, because they evolve over long duration. However, the advantage of the local search methods is if we start from a very good point, we can converge to the final solution very fast. So here that's what we do in hybrid GAs. We start with a GA and let it evolve for some time. So I get a good solution set, which may act as a good initial point when I go for local search methods, and then we can reduce the computational cost. The other one is particle swarm algorithms and ant colony optimization. These all have found or are finding ways in solving multi-objective optimization problems. I think that will be all. If you have some more questions, please let me know.